before the pandemic, it was about Mercury transit and the solar eclipse in 2020. If you remember, it was in October. And after that, we did another Olympiad about the zodiacal signs and the ecliptic. Then we continued doing these Olympiads. The idea of our Olympiad is to make sure that some students who are interested in astronomy to practice some of this hobby. But because too many schools are participating now, actually we are 90 schools, almost 90 to 100 schools now participating in this Olympiad. So we are not able to receive more students, more than 4. Usually we accept 4 to 6 students, but the Minister of Education asked us to reduce the number and to make some kind of competition inside the competition side, so that the final number of schools should be less than 20. But we are not going to do that. So far, we didn't agree with the Minister of Education about that so far. So this Olympiad is again, it is about the sun. It resembles almost the previous one. We did it about 22 and 23. It was about the sunspots, how to observe the sun, how to write a report about, or how to observe the sun safely, and how to calculate the rotational period of the sun. Okay, this is one of the 2 projects. The other project is how to calculate or determine the latitude of Doha. Latitude of Doha is how far Doha is from the equator. So we want to measure this value using something called quadrant. The quadrant is a small t, it's a small tool, it's a quarter of a circle. It was used by ancient and it was developed by Arabs. Arabs have added too many things on the quadrant so that they made it as a calculator. Actually, it is calculating, it is called sine quadrant because it is calculating the sine and cosine of the angles. And I'll show you some curves on the face of this quadrant that from this you can calculate any angles, sine or cosine. And it calculates as well, it measures the height of the objects, it can give the direction of the Qibla, prayer direction of Muslims, and other tasks. So instead of this tool, I am using this tool, okay, protractor, okay, so that the same task I can see or I can measure the height of any object in the sky. This object for this year is the sun. And because we are not allowed to look directly at the sun, we are going to do this in projection manner. So we are going to project the image of the sun on a small piece of white paper. I'll show you outside how to do this. And we are using a line which is freely hand. This line would measure the angle we are measuring for the sun. We will do this, I'll show you how to do this outside. And for the telescope, we will do the projection for the sun so that we can see the image of the sun and the sunspots. Right now, let me tell you what we are going to do about the measuring of the latitude of Doha. One of the most important things to know about Polaris. Polaris is the North Star. The North Star, the height of the North Star above the northern hemisphere or northern horizon, actually it's this direction, okay, almost. If you see the North Star here, Polaris, the height, this height represents the latitude of the city, of the latitude or your location. Almost, because Polaris itself is not exactly located at the pole, the geographic pole, or the celestial pole. It is a little bit deviated. But almost, when you measure the height of Polaris, it is the latitude of your location or your city. Doha is located 25 degrees away north of the equator. So our latitude is almost 25, 23, 25. It depends where you go. But Doha is about 25. Okay. So whenever you measure the height of the altitude of the Polaris, it is the latitude of your place. Why are we doing these experiments? We want to measure the latitude by different methods. Actually, this time we have two methods. The altitude of Polaris, we are not going to do that, and the other one using the quadrant. Again, some astronomical calculation skills, work as a part of team. Okay, look at this, look at the Earth, the globe. It is divided, by circles. These are called the latitude circles. And the main latitude circle is the equator, because it divides the globe into two similar parts, half, upper half, which is the northern half, and the southern half. And away from the equator up, we can measure the latitude. So Doha or Qatar, it is located somewhere here. It is above Cancer, Tropic of Cancer. Tropic of Cancer and the Tropic of Capricorn, they are 23.5 degrees away from the equator. Why? It is as simple as this, because Earth is tilted. The axis of the Earth is tilted by 23.5 degrees. This allows the sun to go up the equator for 23.5 degrees, and it goes down below the equator to the south, again 23.5 degrees. This is the maximum. So it vibrates between Tropic of Cancer and Tropic of Capricorn. In 2 days, it stands above the equator in the two equinoxes. The first equinox is the 21st of March. The second equinox is 23rd of September. So the sun in these 2 days, on these two days, is located almost above the equator. Almost above the equator. Means those people who live on the equator, they should see the sun exactly above their heads in the zenith. Okay? So these people can see the sun going to the south, then to the north. Twice. Anyone lives between the Tropic of Cancer and Tropic of Capricorn must have this phenomenon. This phenomenon at the noon time, in 2 days in the year, he should miss his shadow. Miss his shadow. At the noon time of these 2 days, the sun should be exactly above his head in the zenith, so he will miss the shadow, no shadow. But he should live between the two circles, Tropic of Capricorn and Tropic of Cancer, between these two. I mean, these are the lines or the circles between which the sun is moving. Why is it moving? Because the Earth's axis is tilted. That's why we have the seasons. Seasons are due to the tilt of the Earth. It's not due to the rotation of the Earth around the sun. Okay? Again, one important thing to know, that between equator and the North Pole or South Pole is 90 degrees. It is a right angle between them. It's always right angle. It's always 90 degrees. What does it mean? This mean? This means that because Earth's axis is coming out from this point and from this point, the whole globe is rotating about this axis. It means that this axis is pointing towards some particular point in the sky. This particular point never changes. If it is a star, the star is located at that particular place all the time, day, time, summer, night, whatever. Why? Because this is the direction of the pole, which is now star called Polaris, the pole star, the North Star. Okay? So, between North Star and the equator, there are 90 degrees. It is right angle. You should remember this. So the difference between north and equator is 90. That's why, what is the latitude of equator? 0. The latitude of equator is 0. What is the latitude of North Pole? 90. Isn't it? What does this mean? If I am located on the equator, the North Pole, the star which is called the Polaris, should be exactly on the horizon. Exactly touching the horizon. Because I am on the equator and my latitude is 0, it means that the star should be, North Star should be above the horizon. Okay. Move to the north from equator, move up, till you reach the North Pole itself. Where should we see the North Star? Above my head, 90 degrees. Why? Because I am now 90 degrees away from the equator. So the equator is horizon, North Pole is above my head in the zenith. So what does this mean? It means that the latitude or the altitude of North Pole or North Star or Polaris is the indication of your location, of your latitude. So if I go up to the north, it means it is 90. If I go down to the equator, it is 0. If I am between here and here, it depends where I am. Like Doha, we are 25 degrees. It means that Polaris is 25 degrees above the northern hemisphere. Idea clear? Okay. Because of the rotation of the Earth around its axis, so this is the axis. And this is Polaris. The very first star next to the pole is Polaris. That's why I said it is almost in the pole. Polaris is not exactly at the center or on the center of the pole. It is around. It is almost 0.45 degrees, 0.75 degrees from Polaris, almost less than 1 degree from the pole, the celestial pole here. So this is Polaris, this is the celestial pole. And this is the rotation. Because of the rotation of Earth, we see the stars making trails. And this is very famous photo. I believe that all of you know about it. Okay? So again, the latitude is the difference between the horizon and Polaris, almost. We are going to use, as I told you, the quadrant. We can measure the distances in the sky by different methods. We can use the sextant, the astrolabe. Who have ever seen an astrolabe? Okay, this is a small model. This is a larger one. It's a model. How do we use the astrolabe? It's again easy. Astrolabe has more than 1,000 tasks, but not this one all together, because they are made in different tasks. So one of the easiest tasks, it is a personal watch. 1,000 years ago, this was a personal watch to know the time, to know the direction, to know the sunsets and sunrise, twilight, stars appearing. Because this is a map, actually this is the map of the sky here. This is called red tape, the map. And using this LED or the okay, I can hang the astrolabe freely and check the height of any object in the sky. Then I can measure the altitude of this object. By knowing the altitude of this object, a star or even the sun, I move to the face, the front side of the astrolabe, and change the rectangle or this map till it matches the day I am on. And I can read the sky. You can go through, I did one video, YouTube, astrolabe, Hánي, you can say Hánي, Dali, you will find I'm explaining about astrolabe. I'm explaining it thoroughly. Each and everything, how to use the astrolabe. Okay, this is our quadrant. As I told you, these curves, these are calculation curves. This is sine curve, this is cosine curve, this is time of prayer asr, this is of noon time, this is the freely hand line, and here we look through these two holes again. I'm here going to use a straw. But it is, it's not transparent straw, so that it allows the sun's light to go through. So it is a straw, but I'm not going to use it by my eyes. I'm going to let the sunlight to go through it and project it on, as I told you, a small piece of paper, white paper over here. I'll show you some outside. Okay. 5-6 years ago, we went to Aspire and we went up to the torch to apply something called Al-Biruni's method to determine or to measure the radius of the Earth. Al-Biruni, he was a very smart guy, actually the smartest ever guy Islamic civilization has observed. Al-Biruni discovered, or he made one method, it is some kind of mathematical method, to calculate the height of a mountain or a building, then to calculate the radius of the Earth. He heard that people, ancient people, Al-Khalifa Al-Ma'mun Khalifa, that he measured the circumference of the Earth. He sent two groups of scientists to the north of Iraq, and he asked them to measure the length of 1 degree on the Earth. What does this mean? It means, I'll show you, this one. I look for, okay. He asked them to move from this point to this point. What will happen when they move north? Polaris will rise up. Remember, when we move up north, Polaris itself, it will rise up. At that day, 1,000 years ago, Polaris star was not near pole. It was around 4 degrees away from north celestial pole. So, لطفي كمان أيوة. So there is a very plain desert in Iraq. Now it's in Kirkuk and around that area. Those scientists, they moved 1 degree. Do you know how long 1 degree is on Earth? What is the circumference of the Earth? 40,000 kilometers, isn't it? Divide by 360 degrees, it will give you 111.25 kilometers. 111 kilometers. These people walked on foot. You see? 111 kilometers to measure 1 degree in the sky. Then they went south for the second time. Another team, another group, went south, then north. It means that we have 4 readings. 4 readings. Out of 4 readings, They calculating the mean of these readings. They got a number. Do you believe that this number is correct or wrong? Should be correct, whatever the number is, whatever the result is, but the method is exactly very correct and very accurate. And he got, at that time, the circumference of the earth, but it was a big country, a big khilafat, that they can offer money, scientists, and resources. This was not possible for Abu Rihan al-Biruni. Abu Rihan al-Biruni, he said, I can't afford what Al-Mamun has afforded for scientists and camels, lions, food, and everything. I need to measure it without these means. He invented this method. He invented that he should measure the altitude of the building or the mountain from one point, then from another point, and he would use one equation. He made this equation. Then he went up the mountain. You see, students, they are up the torch. See, the city is down, and measure the depression angle. So depression angle is almost half degree. Then from this half degree and the height of this building, there's an equation. He could calculate the radius of the Earth, then the circumference of the Earth. He was very smart about it. We did this experiment, and almost 400 students went up the torch to the 51st, the last floor of the. You remember seeing the video? So I mean, about 400 students went up the torch to measure this depression angle. It was an amazing activity. Okay, so we can use the quadrant to measure the altitude and the depression angle as well, both directions. This is what I said. This is the sky. This is the celestial pole, which is again the geographical pole. This is the equator, the celestial equator, which is again the Earth equator. But our Earth equator is expanded till it touches the sky. When it touches the sky, we call it celestial equator. Actually, the motion of the sky is a reflection of the motion of the Earth itself, the rotation. So the North Pole of the sky is the North Pole of the Earth, geographical pole. Okay, and so on. And our Capricorn, Tropic of Capricorn or Tropic of Cancer, again they are the same, Tropic of Capricorn and Cancer on the Earth. Same, exact. It means, I mean, that the sun doesn't move above the Capricorn, Tropic of Cancer, or below the Tropic of Capricorn. Now you are asked to prepare this tool. Very simple. You can go to Romnat, buy this tool for 5-10 reals almost. Okay? It's a basic quadrant, just like this. Or you can make your own tool, draw one, larger one, it's up to you. But we are not going to look through. We are going to project the sun's image on the paper, because we are not allowed to look at the sun, because it's very dangerous for us. Now, you will discover that whatever I said is longer many times than what you are going to do. You see, the project or the first project is very simple and direct. There is a free software called Stellarium Web online. Just open it on mobile, and or you can find it on the desktop or the tablet or whatever. Okay? From Stellarium Web, you open the location. Usually we'll choose Doha or whatever, wherever you are. And on the right side, click on the time and date, and choose the time and date. But the time here must be noon time. What does this mean? Noon time is the meridian time. Is the time when you hear Azan al-Dhuhr, when they call Allahu Akbar, noon time. This is the noon time. So at that particular moment, you have to take your measurements. What's the measurement you need to take? Is simply go to the sun, click on the sun here. You will get this window. On this window, you will read RADEC, right ascension declination, DEC. You just read the declination. It is here minus 15 degrees, 26 minutes. Yani almost 15 degrees, 0.5. 15 degrees, 0.5. Because these minutes, 30 minutes means half degree. Okay, so for this day, at this time, the declination of the sun is minus. What does it mean minus? The declination is the distance between the sun and the equator. Nowadays, we are still in the sun is still in the southern hemisphere. It means it is below the equator. We are still in winter, almost in winter. So the sun is below equator. That's why we have the sign negative sign. Okay? You have to take into consideration this negative sign because we have to add it. Simply, when you measure the height of the sun at that particular moment, which is the noon time, okay, I project, there's the sun somewhere here. I project the image of the sun. You can use any stand. You can do your own stand. You can bring a stand from a chemistry lab and just attach this tool on it, okay? And you need that straw. Now, when the image of the sun projects here on the whiteboard, I can read, but this should be freely hand, this weight. This is a weight, okay? I can read the angle. The angle is from this side, okay? I go up like this, so the angle, I can read it from this side, okay? It is almost 50 degrees, almost, say, whatever. It will give me a reading. I need to register the time. The time should be registered, and I'm supposed to do this experiment at particular time, which is noon time on that day. Noon time means the meridian time. It's very easy to know the meridian time here. You can use any software to calculate the meridian time, or the Qatar calendar. Qatar calendar will give you prayer times. The meridian time is Zuhr time, which is calculated. Okay, so at the meridian time, take this reading, prepare it 5 minutes before that. Okay, just prepare your tool 5 minutes before meridian. When it is time, take the reading. Okay, exact. You have a mistake, you can take an error of half degree error. Okay, 41 degrees, 0.5, or 42 degrees, 0.5, something like that. The error should be no more than half a degree. Okay, so take the measurement. Take the reading from stellarium. That's it. This is the project. This is the project. Then calculate. Calculate the latitude. This one. Now, remember what I told you. What's the relation between Polaris and the equator? Right angle. Okay? 90 degrees. Look. So, in Doha, this is the height of the Polaris, the North Pole. It is the latitude 25, almost, isn't it? Clear? The right angle from Polaris is the equator. Is the equator, isn't it? It means that this angle is similar to this angle. 6th grade mathematics. 7th grade mathematics. Very simple. This angle, which is the latitude, should resemble this angle. So I need to calculate this angle, isn't it? How to calculate this angle? It's simply 90 degrees. Look, 90 degrees, this angle. This 90 minus the altitude of the sun, measured by this tool, plus the declination of the sun. The declination of the sun is the distance from the equator, from between the sun and the equator, which is given from stellarium. Now, if the declination of the sun is minus, then you have to subtract it. Okay? So, for today, for example, today, I got this example today. I found that at noontime, the altitude of the sun is 49. So 90 minus 49 is 41. Plus minus 16. 16 is the declination of the sun. Okay, declination is that. So minus 16, I got 25, which is the latitude of Wadar. Now, I advise you to do this experiment or this task as soon as possible. Why? Because you don't need to go under the sun for a long time. Now it's getting hot. I prefer to do it now. The weather is calm. It is accepted, so you can go outside and do this. And we will do it. You got the idea, guys? So this is 90 degrees. I'm targeting this angle. This angle. This is the same. So 90 plus the declination, whichever positive or negative, minus the altitude. Altitude in summer, the sun should be here. But because we are in winter now, the altitude is below the equator. In summer, the sun should be above the equator. You remember this is the equator? So now it is below the equator, it means we are in winter. When it becomes above the equator, we are in summer. Okay, done. Got it? Any questions about this task? So, to summarize, you have to go outside on any day at noontime, measure the altitude of the sun. One task, Second task, open stellarium. On that day, exact day, at that time, choose the time and date, and measure and read the readings of the declination of the sun. Add to the equation, get the latitude of Wadar. This is the first task. Okay, what question? Okay, no question. Say, loudly.
How can I use this projector and astronomy?
We will do this outside. I'll show you. Okay, next is the other task, is how to calculate the rotational period of the sun. And this task already done in the last Olympiad, but we are still doing this because we are almost in the maximum period of the solar activities, solar cycle. So we have to utilize our telescopes to see and project the sunspots, because this is the time of the sunspots. Okay, to identify the solar cycle, learn how to observe the sun safely, study the behavior of sunspots, calculate the rotational period of the sun. Now, I'm not going to talk about the sun, but it's one of the stars. It is the closest star to the Earth, and very almost dwarf star. Our sun is dwarf yellow star. It's not a giant one. Lived almost 4.6 million years, and expected life between 5 and 7 billion years. This is 6 billion years, not million years, billion years. Okay, it is made of almost inner three layers: the core, the radiation layer, convection layer, and outer layers are the photosphere, chromosphere, corona, or coronosphere. They are the hottest layer, actually, the core, and then the chromosphere. Chromosphere is almost between 2 and 4 million degrees, compared to the photosphere, which is 6,000 degrees. And compared to the core, which is 15 million degrees, because inside we've used the hydrogen atoms and get helium, and the rest of the mass converts into energy. This energy comes out as radiation, as light, as temperature, as heat, as whatever. So our sun is very important for our life. Without the sun, no life at all. Very important. We need to follow up the sunspots. Sunspots, they are defined as active regions, magnetic active regions on the surface of the sun. But actually, the region is active below the surface of the sun. They are, some people are defining them as twisting lines of magnetic lines, okay? You know the magnetic lines between the north and the south. They rotate, I'm telling you. Go ahead. See, I will tell you, I will come back. So this sunspot starts appearing from the eastern limb of the sun, and it moves, then it sets at the western limb of the sun. We are going to follow up one of these, two of these sunspots. The rotation of the sun is called differential rotation. What does it mean? It means that it is very fast. The sun, because it is not a rigid body, it is called the fourth state of plasma. It's called plasma. So it is rotating very fast at the equator and slowly at the poles. Between 25 days, one rotation, and almost 35 days. 35 days. So this is called differential rotation. Due to this differential rotation, the magnetic field lines reaching from north, connecting between north and south, they are twisted. They are forced to rotate at the equator faster than the upper latitudes. So they start rotating faster than themselves up. They are twisted. Then when they are twisted, they are cut. When they are cut, a sunspot appears, or a filament appears, or some solar flares appear, or some giant prominences appear. So these particular points, they are the cutting or twisting of the magnetic field line. So sunspots. They appear above the sun colder than the rest of the surface. Almost they are 4,000 degrees. This is called the umbra, the shadow. The surrounding areas, penumbra, are almost 5,000 degrees, and the yellow surface of the sun is almost 6,000 degrees in temperature. So this is the how to calculate. We want to calculate or to just write down how many days it takes with the sun to rotate. But as I told you, rotation of the sun is not one rotation. It is differential rotations. It means that what we are going to calculate is the rotation according to the latitude, with respect to latitude, okay? Compared to the planets, sun is almost the giant object in the solar system. It's almost 99% of the mass of the solar system. Where's the Earth? Is somewhere? No, Earth is here is very large, by the way. It's not correct. It should be 109 Earths. Should be 90. 109. This is more than that person. Okay, due to solar activity, what we call solar cycles. Solar cycles, each solar cycle takes almost 11.2 years. In this solar cycle, we can see sunspots, and we can see no sunspots. We call minimum solar cycle or maximum, the peak. We are almost around the peak. The peak of our solar cycle, now it is 25th solar cycle. It is almost will be next year, July 2025. This will be the peak, the highest or the maximum of our solar cycle. Then it will deviate or decline after that. So almost in 2020, between 2018 and 2020, there was no sunspots at all. The sun was so clear, not even single sunspot. It's called minimum activity, minimum solar cycle. But nowadays, just go outside, you will see every day more than one sunspot. And we are expecting this scene or this figure or this picture to be repeated maybe next year. Okay. At the beginning of the solar cycle, which started 2020, 2021 almost, most of the sunspots start appearing highly above the equator, almost 30, 35 degrees latitude. And by advancing, with time advancing moving, the first year, second year, third year of the solar activity, the sunspots start appear closer and closer and closer to the equator. At the maximum of the solar activity, most of the sunspots appear around equator. Remember this. So they start appearing up, now in the middle, then at the equator. This can be drawn as what is called Maunder's butterfly. So each butterfly is one solar cycle. See, 1880, 1890, 900, 1910, and so on. So the sunspots almost start appearing at higher latitudes, and with time they come closer to the equator. The end of the solar cycle, almost the solar sunspots are appearing around the equator of the sun. Okay, this is the historical drawing of the solar cycles. Our solar cycle, as I have told you, almost here in July 25. Expected. Now, what we are going to do? Open the website called spaceweather.com. I'll send you all material and literature. When you open this website, you will find this date. Here the date, time, okay, February 5 and 2021. You will see this window. This window shows the image of the sun, today's image of the sun. Just click on it, it will fill the screen, and you'll see all sunspots. Each sunspot is numerated, it is given a number. This number depends on time. I mean, every day they give 1 or 2 or 3, depends on how many sunspots are appearing. Sunspots are appearing in 2 manners. Either they are single sunspot or they are group. That's why they are called active regions. Active region here, this one is 30-30 AR. It's called AR 30-30, 30-32, 30-33. 30-34, 30-35, but here 30-36. Although the sun rotates from left to right, and 30-36 should be here, not here. But because sunspots can appear anytime, on any place on the sun, we can't expect that. It's just like a meteor shower, meteorite, or a meteor. You can't expect the meteor, shooting star. When it comes, at what time, which direction, you can't expect it. Like beta inverse decay, you can't expect it. So this one appeared when the sun almost was about to set. Okay? So this appeared. But this appeared after this. After this. This 37 again. 37 again appeared after 36. What we are going to do, follow up two of these sunspots. Go back in the date. You are allowed here to go back. This is February. You can go many years back. But too many years is not good. You maximum last year because you need to see some sunspots. Almost sunspots are now appearing this year, last year, almost 2 years ago, and next year. Next year you can't see because it's still the future. Okay? Go. Follow up one of the sunspots. Now see, I'm going to show you. Look. It is rotating. Look at this sunspot, or this blue, this one. Okay, now it is disappearing. Okay. Now it is disappearing. It appeared. Now, follow. How many days? The software or the website allows you to see all images of this sunspot. All images. From the very moment it starts appearing till the end when it disappears. Okay? So you can take the date, first day and last day, calculate the duration between these 2 days. You have to do this for 2 sunspots. When this sunspot reaches the center of the sun, I mean the center line, because should not be at might not be here, somewhere on this line, you measure the latitude of this sunspot. How to measure this latitude? Use this diagram. Use this diagram, apply it above the solar image, the sun image from the website. You can read. So this sunspot, it reads 0, 10, 20, 25, minus 25 degrees, or 25 south of equator. You can choose one here and another here. Now, by following up the time from the beginning of appearance till the end of disappearing, you can get some time. See this one. For example, this sunspot 3089. Okay, we calculated the days from the beginning to till the end, 13 days. Multiplied by 2, it is 26. The latitude is 25. This one. This one. Here, 3089. This one, 3089. 3089. 3089. This one. So the latitude is 25 to south. This is the 3089 and so on. You have to do this for 2 sunspots. Very easy. Very easy. Just go to the website, choose any 2 spots on any days, past days, of course, they should be past days. Calculate the very first beginning and the very last ending, disappearance, and just fill in this term. But you have another task. The other task is we will go outside, project the sun's disk on the paper, on the white paper here, see the sunspots, take a group photo, and take a photo for the sunspot itself. That's it. 2 things. Again, project, let the students stand behind the whiteboard, and teacher will take the photo from here. So the photo should include telescope, projection, and the students. This one photo. For the girls, these photos are for evaluating, not for publishing. Okay? So you can use masks, you can use your bags, whatever. I need to see you with the sunspots. So 2 things. one photo, close photo for the sunspots. It should be focused, and I'll show you how to do it focused. The other one with tilted. Now, like this, yesterday we were students, girls students were here, and this is the telescope, this is the projection, this is the group photo. The second photo is this cut. Clear, easy, صح? Last thing. How to promote this knowledge at your own schools, because you are few students. I need and we need to promote this knowledge to others. Many students are interested. Maybe they are keen interested in astronomy, but they are not allowed. They don't have the chance. They don't have the time. So what you are supposed to do regarding this task, two things. You have to prepare a presentation about the sun. I'll send you one presentation or two presentations. I'll send you the Arabic presentation. It's better than mine, of Dr. Bashir. Change it into English, it's easy. Use the photos and the animations. And target 200 students from your school, if they are 200 or whatever. Once, twice, thrice, whatever. I need at least 200 students to listen. You, who are you? The 4 students. Now you are 4. So 4 students should come to the stage and one by one should tell the other students about the sun, how to observe, how safely should we observe the sun, and we have to take our telescope outside and show them the sunspots. Now, if you don't have a telescope, you have to manage that. Take them to another school, borrow a telescope from a student, buy a telescope, whatever. But you have to do this activity. Okay? It's not difficult. So this is the first. Or you can ask the students to come to the auditorium one day to give them one lecture, another time, another lecture, another time. At least 200 students should be targeted. And you have to document that. You have to show me the photos for the students and for the lecturers, before educators, before students who are giving these lectures, okay, or part of these lectures. Second one is to take your telescope, as I told you. No less than 100 students should see sunspots, okay? Either by projection method, or if you have a telescope with a filter, they can see through the telescope, but the filter, solar filter, should be put on the telescope. Otherwise, it's impossible. Don't look at the sun. Don't allow anybody to look at the sun. Never allow them to look at the sun with their bare eyes, okay? So this is the second task. Some schools, they don't have 100 or 200 students. It's okay for me. Just you can target whatever number. But if you have more students, please target more students. And I'm saying 200. If you can target 1,000, it's okay for me. It's okay for me, and it's good for you as well, and for your teacher, because it's very, very, very interesting activity. Okay, this all what I have today. Please, we will now move outside to do the practical part of these two experiments. Done? Any questions? Fine. Assalamu alaikum.